Hey everybody, welcome to another day of physical science. We're going to start by talking about a new unit called matter. So, first thing you need to know about matter is anything that takes up space and has mass. So, usually at the start of the unit, we do this big thing about like, hey, is this matter? Is this not matter? Can you come up with some ideas? What I'd like you guys to do right now in your head is take about a couple seconds, maybe 30 seconds, and think of one example of something that definitely does take up space and definitely does have mass, and try to think of another thing, or, yeah, thing is about as much of a hint as I'll give you, that doesn't take up space and doesn't have mass. Can you think of something like that? Cool. Okay, so matter has a bunch of different classifications, and of course, as scientists, we're going to classify it because that's what we do. That's how we be. So yeah, let's just get into it. There we go. Matter. Boom. That's the big overarching category. And then we've got a bunch of smaller categories like things that are pure versus things that are not pure. Um, yeah, when we're talking about pure stuff, we're usually talking about chemicals, or even more specifically, atoms and elements. Maybe you've heard of a periodic table of the elements. That's something that we do a lot in chemistry. Woohoo! And then mixtures are kind of anything that's not pure. So there's even more topics from there. We've got elements and compounds. Compounds are pretty much just chemicals, two or more elements mixed together. For mixtures, we've got homogeneous mixtures and we've got heterogeneous mixtures. We'll talk more about the difference between homogeneous and heterogeneous. We'll talk more about the difference between mixture and pure substance, and more about the difference between element and compound. But I wanted you guys to see right away that there's a lot of different ways that we break up matter. Things that are not matter, mostly we would say are energy. Things like ideas, heat, cold, um, lights, that sort of stuff. Yeah, all that sort of stuff is energy. So, okay, pure substances. A substance that cannot be broken down, or sorry, let me reread that. Can only be broken down by chemical means. These are pure substances here. We got two kinds. We've got elements and we've got compounds. Elements are one kind of atom or one kind of molecule. I should change that. That shouldn't say that. That should just say one kind of atom. I know this is very thrilling for you guys. Sorry, one kind of atom. Compounds are more than one chemically combined element. So right away we'll notice a difference in terms of numbers of capital letters in their formula. An element will just have one capital letter in its formula, so something like O is the element oxygen, or something like Fe, capital F, lowercase e, is iron. Those are both elements, for example, but compounds could have something like Fe2O3, which is iron 2 oxide, iron 3 oxide, which is rust. Fun fact, in case you were wondering. But yeah, so compounds, more than one chemical element, just one kind of chemical. That means one capital letter for elements, more than one capital letter. Elements are found in the periodic table. Compounds are not. They're just chemicals found in everyday life. That's water, that's lye, and that's sugar, in case you were wondering what these three chemical formulas were. Here's what an element looks like on the periodic table. Here's an example of a chemical compound. This chemical compound, in case you're wondering, is caffeine. Fun fact. Oh, I have it written down there. Okay. Anyways, element versus compound. Elements are found on the periodic table. Compounds, they can look like this, or they might look like this, a slightly different white substance. Or they might look like a cube of sugar, or maybe they look like, I don't know, this red stuff or this blue stuff. Elements tend to mostly look like metals. Silicon's actually a metalloid, but that's not really important. They can sometimes look like liquids or even liquid metals. So yeah, kind of cool. But elements are all found on this periodic table. Compounds, most of them tend to look like some sort of powder. Um, yeah. But either way, you'll notice that these all look like they're pure things. None of these things look like it's something mixed with something else. Okay, so here's kind of a visualization of an element. Here's a visualization of a compound. How is this a good picture? How is this misleading? Well, it's a good picture because it shows that elements all the same thing. Compounds look like it's two or more different things combined together. But you might think that this looks less like maybe just like pure cookie dough, and maybe looks more like chocolate chip cookie dough. But realistically, a compound is also looks uniform. Mixtures, a substance that can only be broken down by physical means. We've got homogeneous and heterogeneous. Homo means same, so homogeneous mixtures are going to all look uniform. So a lot of times you might mix up a homogeneous mixture and a compound just because if you look at them without doing any sort of testing, it just looks the same. Heterogeneous is going to look different, like sand and water. Silicon dioxide is the same thing as sand. So sand and water versus sugar water. Sugar water, this looks like pure water. You wouldn't necessarily know that this was a homogeneous mixture unless I told you, which I did. Anyways, so yeah, homogeneous are uniformly distributed. Homo means same, and heterogeneous means not uniformly distributed. So you might have stuff settling at the bottom, or you might have layers, or I don't know, something else. You might have big chunks of stuff. Okay, homogeneous mixtures, we have things like stainless steel versus heterogeneous are things like oil and water. Here are some other examples. You can read them. Bears are heterogeneous mixtures, fun fact. Hope you guys all knew that. Salt, water, air. So these are all things that maybe you might not have known are actually not elements, unless you actually spent enough time looking at the periodic table, or if someone told you what the chemical compound was. Stainless steel is a mixture of iron and carbon, fun fact. Bronze is a mixture of like copper, zinc, tin, other things. Salt water is salt and water. And air is actually made up mostly of nitrogen. Bet you didn't know that. Bet you thought it was oxygen. Yeah, it's nitrogen first, then oxygen, then carbon dioxide, or sorry, then water vapor, then carbon dioxide, then a couple other stuff, a couple other things. Yeah, so hopefully what I want you to see with these two pictures here, homogeneous, notice that the little purple things are kind of evenly distributed, whereas in heterogeneous, you got big clumps of stuff, not the same, more like different. So het means different, homo means same in Latin, in case you were wondering, because I speak Latin. Not really. Okay, what's the difference between a mixture and a pure substance? You can change a mixture's properties by filtering or distilling. Those are two ways. Also, mixtures are separated by physical means. Pure substances, separated by chemical means. Right? Huge difference right there between the two. Mixtures are physical means only, so things like filtering, distilling. It doesn't change the stuff that gets filtered or distilled, right? Like let's say you filtered out sugar from your sugar water. You would still, like the sugar would still taste sweet, the water would still taste like water, I guess. Yeah, anyways, it wouldn't really make a difference. Pure substances, you can change them by reacting. Is one way. So yeah, notice how if you're reacting, you go through a reaction, poof, you get new compound or new elements that combine in new ways. It's totally different now. So yeah. Okay, properties of matter. Physical properties are characteristics that can be observed without changing the matter. Chemical properties are characteristics that cannot be observed without changing the matter. So, you might be wondering, what are some examples of physical properties? Things like size, mass, volume. You can weigh something without changing it. Now, chemical properties would be things like flammability or reactivity. You can't really judge how flammable something is. You can't test how flammable something is without actually setting it on fire. Even if you know something like oil is flammable, it's because someone at some point in time set it on fire, right? So chemical properties are properties that we'd have to observe by first changing the thing. Let's say hardness. You might be thinking, well, Mr. Smith, if I'm testing how hard wood is, I'm going to have to break it, right? That's changing the wood. If you break a piece of wood, you still have two pieces of wood that are still wood, right? If you set a piece of wood on fire, what you end up with is not wood, it's charcoal, which has different properties, different chemicals, different makeups, and stuff like that. So, chemical properties change the stuff in order to observe it. Physical properties, you can still smash stuff, but it's still the same type of stuff that it was before. There's no chemical change. Okay, physical changes don't change the matter. Chemical changes change the matter. That's the huge difference there. So anything that you can do with a bone, like break, tear, cut, or I guess you can't melt a bone. Yeah, you could. Breaking, tearing, and cutting, those are things that are physical changes. And then phase changes. Phase changes are things like boiling, evaporating, condensing, and anything where you go from like a solid to a liquid, or a liquid back to a solid, or a liquid to a gas, or a gas back to a liquid, that sort of thing. Chemical changes, we're thinking of things like burning, digesting, reacting, spoiling, if food spoils, if it goes rotten. Yeah, those are all examples of chemical changes, right? You might eat a grape and it comes out as poop. It's different now, right? States of matter, we got solids, liquids, and gases. What? There they are. What I want you to notice here, solids are very close to each other, liquids not as close, and gases are very far apart from each other. So as we go from a solid to a liquid to a gas, the particles move apart. And they also start moving faster. That's one of the things you won't see in these pictures. Solids move like this, liquids move like this, and gases move like this. They move even faster. Fun facts. Solids have fixed shapes. Liquids and gases do not have a fixed shape. Think about it. If you pour a liquid into a bag, you can make that into whatever shape you want. Or if you put gases into a balloon, you can then turn that balloon into whatever animal. If you drop a brick into a balloon, which how would you do that? But if you managed to, you could not then turn the brick into a balloon animal. It just wouldn't work, I think. Anyways, solids have fixed volume. Liquids also have fixed volumes. You can't compress them. Normally what I do is I take a syringe, just imagine I had a syringe here, and then you can do that with air, actually. You can kind of like shrink it. But if you take liquid and you try and do that, like for example, grab a plastic bag, fill it up with water, seal it tight, and then try and close it. What'll end up happening is that the liquid will explode into your face, and then I'll laugh from a distance. But gases don't have a fixed volume. If you take that bag full of gases, you can actually shrink it a little bit, which is fun. Cool party trick at the very least. Yeah. Solids particles move slowly, liquids particles move, and gases particles move fast. Notice again here, they're picking up speed as we go from solids to liquids to gases. Okay. Questions that kids asked me last year. They were like, hey, is Play-Doh, clay, Jello, what are they? Liquid, solid, what's the deal? The answer is yeah, we're not really sure. Okay, that's all the time I have for you guys. I hope that didn't answer any of your questions. Actually, no, I don't. I hope it answered a bunch of your questions. I hope you had fun. Thanks for a great lesson. Have a great rest of your day. See you later. Bye-bye.